Okie doke. So we're going to solve this problem in 2 steps. First, we're going to concentrate totally on the first phase and not worry about everything else. Okay? We're going to concentrate on the first phase, and we're going to seek the final velocity. Once we have that final velocity, we're going to set it equal to this initial velocity over here for the second phase, and then we can solve the second phase of the problem. This number here we're looking for, the maximum x, is a second phase number. It's that number right there. But we can't just find it immediately using these equations, so we have to do the 2 steps. So first, let's look at just the first phase and determining what v is. We know x naught, we know x, we know v naught, we know a. Which of these 3 equations is going to help us determine v, given what we have? Well, it's not 2 or 3, because both 2 or 3 involve it's not 1 or 2. Pardon me. Which equation do we use to find v? It's not 1 or 2, because we don't know the time for phase 1, and the time shows up in both 1 and 2. It's going to be number 3. Right? We're trying to find v. Okay? We know v naught, we know a, and we know x, and we know x naught. We know everything but v in this equation. So the phase 1 question, okay, so phase 1, finding v, we simply use this equation here. V squared is v naught squared plus 2ax minus x naught. We use the third equation. And some of these things, as almost always happens, but not every time, are 0. V naught is 0. This term goes away. X naught is 0, so that goes away. And we're left with something very simple. V squared is 2ax. So v is a square root. Like that squeaky sound? That's awesome, isn't it? Is square root of 2ax. Now we can plug our numbers in. 2 times a is 12, and it's positive meters per second squared, times x, which is 29 meters. Put it in your calculator, crunch the numbers, and you get 26.38 meters per second. Okay, that is the final velocity for phase 1. That's this number right here. 26.38 meters per second. Now, I kept 4 significant figures there because that's not our final answer. We want to keep 1 or 2 extra significant figures, and we only cut at the end. We're going to cut to 2 because we're given 2 significant figures here and 2 there. So in the end, our number is going to have 2 significant figures. I kept 4 here just to keep it nice and precise as we move through the intermediate stages of the problem. At the end, as I told you last week, we're going to do the cut for significant figures, but only at the end. So if this is how fast the rocket is going, 26.38 meters per second, at the end of phase 1, that is also precisely how fast it's going at the beginning of phase 2. So we can now come over here and say that the final velocity for phase 1 is the initial velocity for phase 2, 26.38 meters per second. Right? In the same way that our final position for phase 1 was the initial position for phase 2, our final velocity of phase 1 is our initial velocity for phase 2. Okay? So now we have enough information on the right to find the thing in pink we're looking for. Okay, so we had to do some phase one problem solving in order to get to the answer. But this is an intermediate step. That was the phase one math. Give me a second to erase this. There's no way I had enough space on the board to do all of this at once. So now what we have is we have phase two. Now we know 4 out of 6 things, which is enough. Okay? So we're looking for x. Which one of these are we going to use to find x? Given what we know. We know x naught, we know v naught, we know a. And we're trying to find, and we know v. So we know x naught, we know v naught, we know v, and we know a. In the second phase, the rocket's slowing down, remember? So its acceleration is downward. If an object is slowing down, that means its velocity is opposite the direction of its acceleration. So its acceleration during the second part in free fall is down. We know 4 things. Which equation do we use? Well, we don't know time again. And look, this equation, number 3, has 1, 2, 3, 4, 5 quantities in it. It's got 5 quantities. It's got the 4 that we know and the 1 we don't. And the 1 that we want to know. It's got 4, it's got velocity, initial velocity, acceleration, final position, initial position. We know of those 5, we know 4 of them, and the 5th one is the thing we're looking for. So again, we're going to use 3. So this is phase 2. Let's write the equation down again. V squared, v naught squared, plus 2ax minus x naught. Okay. So which of these is 0? Only one is. That's the final velocity up here at the top, right? So this is 0 on the left-hand side. Oops, I should have made that pink. I'm trying to keep this all, color-coded, coordinated. So that is 0. Okay. So we need to subtract v naught squared from both sides. So minus v naught squared is 2ax minus x naught. We're trying to find, remember, not to beat a dead horse, we're trying to find x. We're trying to solve this equation for that x right there. The next step in the algebra is dividing both sides by 2a. By doing that, we now have eliminated 2a from this side. So we've got negative v naught squared over 2a equals x minus x naught. I'm going to flip the 2 sides because I can, and because we're looking for x. So I'm going to write it this way. X minus x naught is minus v naught squared over 2a. All I did there in that last step from here to here, it's like saying if x equals y, then y equals x. All I've done is flip the 2. If 2 plus 2 is 4, then 4 equals 2 plus 2. I've just switched the 2 sides, that's all. And we're looking for x again, like that's the quantity we're looking for, so we need to add x naught to both sides. So we get x equals x naught minus v naught squared over 2a. And remember, these are all phase 2 quantities. So now we can plug in numbers. 29 meters, right, that's x naught. For phase 2, 29 meters, minus v naught squared. Well, v naught is what we just found, 26.38 meters per second. That's squared over 2 times a, which is negative 9.81. Oops, left my units off. meters per second squared. Okay, so that's 29 meters. You're going to get a plus sign there. Why? Because you've got a negative sign here and a negative sign in the basement, and they're going to cancel. You have minus a minus number, minus a negative number, right? So minus minus 2 is the same as plus 2. That's what's happening here. 29 meters plus about 35 meters gives us a grand total of 64 meters. And that is the answer. X is 64 meters. So it goes 29 meters as it accelerates upward, but it keeps on going. It's not just going to stop right when the engine cuts out, any more than the pin stops when I stop moving my hand up, right? I stop my hand, but the pin keeps moving up, right? The pin is moving up. When I stop, see, watch that. I'll pull my hand up, then I'll stop it, and the pin will keep going. See? So even when the engine cuts off, and it's no longer being pushed up by the engine, it's going to keep moving. And when it does, it's in free fall. And as it slows down, it increases an extra 35 meters. So it goes 64 meters up before falling back down to the ground. That's a two-phase problem. To recap, that was a two-phase problem, and we applied our equations of motion first to phase 1 and second to phase 2, because the equations of motion only apply for constant acceleration. And overall, this is not a constant acceleration deal. Acceleration changes from 12 to negative 9.8. But taken individually, these phases are constant acceleration deals. And so we can apply these individually to phase 1 and phase 2 and build up to the answer. Okay? And you can do this in horizontal dimension as well, not just vertical. I mean, this sort of two-phase trick like this. Okay, you'll see it again. Wink, wink, nudge, nudge, hint, hint. All right, that's it for chapter 2. That's it for one-dimensional motion. Next up is going to be sort of mathematical, some recreational mathematics, okay, on vectors. But that's for next time. I'll see you then. Be well.